Okay, off we go. So last time we were talking about this theorem right here. This is an old theorem from single variable calculus, and it turns out this generalizes very nicely to a multivariable result. We didn't quite have time to get to that last time, so that's where we're picking up. Real quick, there's a Riemann sum point of view justifying this, of course. Roughly speaking, the terms kind of pair up and cancel. Right? There's also a point of view of using a substitution that also works, which of course is kind of a change of variables, and that's why this is ultimately in the section on change of variables. But again, tough choices and all that. Okay, picking up next with the two-dimensional version. The idea here is just to generalize what we mean by taking the x value and flipping it over the origin to get negative x. We're going to call that a reflection. It's like you're reflecting over the origin. And that's something we can generalize. Right? So if you look at this picture right here, there's some details of how to think about this geometrically, which I think is not something we really need to go into. It's exactly what the picture looks like. It's exactly what you would expect a reflection to be. That's going to be good enough. With this in mind, we can generalize all of the ideas that we use to build up this symmetry theorem. So in particular, we can talk about a function having odd symmetry over the line. And the idea of odd symmetry over the line is that when you reflect, the result is a minus sign on the value of the function. So when you reflect the input, you negate the output. So really just kind of a same idea as single variable oddness, just generalized for this two-dimensional idea of a reflection. You can also generalize the idea of a symmetric domain. Now how we write that down in notation, nothing to worry about. I felt obligated to write it down, but this isn't something we're going to get into the weeds on, so don't worry about that. A symmetric domain means exactly what you think it means. It means that when you reflect the entire domain over the line, it looks exactly the same before as it did after. Okay. All right. So with that done, here's our theorem. It's exactly analogous to the single variable theorem. In particular, if you're looking at an integral, and if your integrand is odd, and if your domain is symmetric, then your integral is equal to 0. And what's beautiful about this is you don't have to slice this up and turn it into an iterated integral. You don't have to then subsequently do a couple of separate anti-differentiations, right? You don't have to worry about the possibility that as you sliced it, you might have sliced through a corner and you might have to do the whole thing twice, right? None of that comes up if you just establish these two conditions. Snap your fingers, declare victory, integral 0. It's really awesome. Very convenient when it comes up. Okay, now a couple of warnings. You do have to be careful about this. You do need both of these conditions. This is really, really important. Very often, I see this so often, and it's tragic every time I see this. Students will see a symmetric domain for their integral and just think, oh, symmetry theorem doesn't work. You've got to have both conditions. The integrand has to be odd also, yeah.
So the fact that it's odd, like it would cancel out, which is why it's equal to 0?
Yeah, that's right. In some sense, you need the oddness so that you get the cancellation. You need the symmetry so that the terms in the Riemann sum will kind of pair up together, and then you need the oddness so that they'll cancel. Okay. Yeah, that's right. So make sure, don't step on this landmine. Don't look at a symmetric domain and then just assume, right, that you can just invoke a symmetry theorem. It just doesn't work. It makes no sense at all. So easy mistake to make. Also, and even more subtle, you've got to use the same line for both of these symmetries. That's, again, that's a critical detail, but easy to kind of subtly overlook. So heads up about that as well. Now, why is this theorem true? Well, again, there's different ways of looking at it. There is a change of variables point of view. Roughly speaking, you use the reflection itself as a change of variables. And when you do that, and you do the corresponding pullback, it turns out the answer falls right in your lap. This is unfortunately something we don't have time to go into. You're not responsible for it either, so you don't have to worry about this if you're not interested. But if you are, I think it's a pretty cool argument, and I encourage you to take a look. What I think is a little bit more relatable, a little bit more visually sort of there it is the Riemann sum point of view. And you can kind of see that if you have a symmetric domain, as I've attempted to draw here, competence aside, terms of the Riemann sum are going to pair up. Every term has a corresponding other term, sort of a reflected term, right? And then they cancel because of the minus sign that you get with the oddness, again, that we talked about before, just like with the single variable case. Okay. All right. So let's see an example. Oh, yeah.
Do we get to pick L?
Yes. That's a good thing and a bad thing. It's a good thing because it gives you a lot of flexibility. It's a bad thing because you really do have to decide. Right? Yeah, absolutely. So, let's apply this idea to this integral here. Right? We've been asked to compute that integral. And let's take a quick moment to recognize what a nightmare this would be. Right? And it's tempting to just look only at the integrand and already be kind of weirded out by the fact that there's an exponential with a quadratic in the exponent, but then furthermore, there's this factor out front, so you're thinking probably integration by parts and substitutions and stuff like that. But don't forget that you're also going to have to deal with the domain. The domain has some algebra in it. The algebra there is going to work its way into the integrand for the outside integral. We've seen that happen a million times. So it is quite a bit worse than it looks. So this is a really unpleasant integral to compute directly. And we definitely don't want to have to do that. That is, if it can be done at all. And I have to confess, I haven't worked this out. I'm not sure how doable this is, but kind of moot. But I'm not entirely clear this is even a doable integral. All right, so with that comparison point established, let's think about what we're looking at here. Let's draw our domain. Let's draw these two curves right here. And I'm just going to make a sort of a rough drawing of these. There's this curve, which looks approximately like that. Flashbacks to Calc 1, right? Hope everybody remembers how to plot curves, and this is what that one ends up being. And then there's this curve, y equals -1. That's an easy one, something like that. And so you see that our domain in question here, the region that's bounded by those curves, is this region like this. And now I'm going to make a geometric appeal, symmetric. Right, you can kind of just see it right there in the picture. Now, if you want to get, rigorous, right, if you want to see some details to establish that this is symmetric the way you think it is, first of all, let's notice the symmetry is like this, like I'm doing with my hand here, namely by way of a reflection over the y-axis. Right, that's the symmetry I'm claiming. It's not symmetric this way, right? It's definitely over the y-axis. Let's think about what a reflection over the y-axis looks like. This is what it would look like to reflect over the y-axis. And if you think about it, notice whatever point I reflect, you look at the reflection point also, they're going to have the same y-coordinate. And the only difference is they're going to have sort of opposite. They're going to have negative x-coordinates of each other. So this reflection is described by that function right there. Does everybody buy that? That's kind of a geometric appeal. Yeah.
So would your line here be the y-axis?
Yeah, the line of symmetry is the y-axis. That's right. Symmetric over the y-axis.
Which is why we can choose our line. Like that's why it helps. Like
I didn't follow.
because you said like if like we have to. We get to choose our own line,
Yep.
and that's a good or bad thing.
Yeah, it's good. That's right. So you do have to have the insight to look and identify that this is the correct line, right? So you can't just say I'm going to be a reflect over the x-axis kind of person, and this is always reflect over the x-axis, because lots of domains, for example, this one simply aren't symmetric over the x-axis. You do this, it's just not the same. So so there is this geometric sort of obligation to look and understand your domain and identify with geometric intuition what line is it that'll work. Sometimes you have a choice. Sometimes there are several that'll work.
That's what I mean. Like when we have a choice, meaning we can pick like several. Is there a better option than the other?
It's got to work with all of the conditions of the theorem, and that's going to be the tricky bit. We'll get to it. Yeah. Okay. So we've identified a line of symmetry of the domain. We've identified the corresponding reflection, and again, if you want to try to persuade yourself that this actually works, notice what I did here. I actually incorporated the reflection. Notice the reflection, what it does is it turns, wrong color. The reflection effectively turns the x-coordinate of the input into minus x for the output. And notice I kind of did that here, like so, and notice the result is same curve. So this curve is its own reflection over this y-axis, and pretty easy. You don't need any fancy algebra to persuade yourself that the blue line also, right, is its own reflection, and it follows then that the region in question is symmetric. Yeah? Everybody happy? Okay. Now, next we have to establish that the integrand is odd. And how do we establish that an integrand is odd? Well, go back to the definition. We need to take the reflection. We need to plug in that reflection. Now, that's all I've done in this first step here. I've just taken this formula for the reflection that I saw from the picture. Plug it in, and we're going to do the algebra and see if we get the minus sign that we need to get. And now you can look ahead and see, it's going to work out. Right? For this function, when you plug the reflection in, you get a negative out. But let's go through and think about how that algebra works. And there's a little bit of a tricky bit here. Let's see here. Let me just get rid of the mess here. Okay, here's the tricky bit. This is my F. You know what? Bad color choice. Let me try it. Let me do it like this. F is that. I've got to plug in the reflection. Keep in mind what this means. When I say negative x is the input, or is the first coordinate of the input, got to keep in mind the formula that we're looking up here at, right? X is the first input, y is the second input. If I were to write this as, f of x comma y, it would be f of x as the first input and y as the second input. So when I say we're going to plug in minus x as the first input, that means minus x is going to go where x is. Like so. Everybody follow that? Okay, so this is, algebraically, this is what it means to plug in the reflection into the function that I'm going to try to establish as being odd. Okay, and having done that, there's a little bit of algebra to be done. This is no big deal, but this is equal to this. Again, total high school algebra. Y'all can think through those details. And the punchline is, sure enough, as we needed it to be, this is the negative of the regular value of the function. So the function's odd. Everybody see the process? All right, so game over. We win. This integral is 0. No further calculations required. This integral is 0 by symmetry. And that is way, way less work than it would have been had we done this the old-fashioned way, right, as an iterated integral. Everybody see that? Big win, right? Okay. All right, so now I encourage you to use symmetry arguments. I am a big fan of symmetry arguments, and just to let you know why I'm such a big fan. I, believe it or not, used to be an undergrad too. When I was an undergrad, I took a lot of courses that were not that different from the engineering courses that most of y'all are going to be taking in the next few years. Mine were in physics, but it's not that different. And I did bazillions of integrals, double integrals, triple integrals. Bazillions of them, right? My back of the envelope kind of estimate, just kind of based on memory and that kind of thing, I think conservatively I would estimate 20% of the integrals that I encountered equal to 0 by symmetry. I think that's a conservative estimate, right? So I took 9 physics courses as an undergrad. That means 1.8 conservatively 1.8 full physics courses worth of integrals. 0 by symmetry. It's a really big deal. Everybody see that? Okay, so be on the lookout for this. Again, huge fan, and I strongly encourage you to do it. Now, that said, I do require that you give me reasonable mathematical arguments. Again, we're not interested in answers, we're interested in reasoning, and this is what I consider to be a complete argument that uses symmetry. You just got to flesh out the details. Kind of like in the example we just did. Make sure that you actually tell me what line of symmetry you're using. It's kind of a big deal, right? It's sort of fundamental to the entire argument. Don't leave that little critical detail out. You got to tell me. We're going to need the reflection formula, so you got to write that down. An explicit formula for the reflection. Notice it's again just a cornerstone, essential aspect of the argument that the function is odd. So you got to tell me so, right? You got to make the recognition, right? Doff the cap, right? Acknowledge the relevance that the function's odd. Half of the point, in some sense, is that the function is odd. By the way, you also have to be right about that, right? You can't just go around claiming stuff's odd and hope for partial credit on something if it's not, right? So you do have to be right about that, so heads up. And by the way, you also have to demonstrate that the function is odd. It's not enough to say it and be correct. We need to know why. It's typically not very obvious. For example, you look at this function up here, it's not just perfectly obvious that this function is odd in any sense, much less in whatever specific sense you need it to be. Right? So again, something that's got to be shown, like we did there. And then lastly, you got to, again, doff the cap. You got to acknowledge how important it is that the domain be symmetric. So you have to actually tell me that the domain is symmetric. And again, you got to be right about it, right? Notice, though, absent from this list, you don't have to demonstrate that the domain is symmetric. That's usually geometrically pretty obvious. Any algebra that would go into doing that is mostly just kind of formalities that I just don't think that's enough of, I think that's just a little too off from what this course is about, and I'm not worried about it, and so I absolve you of responsibility for explaining why the domain is symmetric. But you do have to tell me that it is symmetric. Okay, so do make sure to give me all 5 of these if you want full credit for your argument. Again, it's not about the answer. It's not enough to be right? You got to give me the valid mathematical reasoning, and this is what I think is appropriate for this context. Yeah.
For observing that D is symmetric,
Yeah.
is a graph enough, or do we actually have to state that D is symmetric?
You got to actually say it, and I think you're going to have to draw a picture anyway, just to convince yourself, right? But yeah, it's you just have to state it, and you got to be right. Yeah. Okay. All right. Now, a worry, something to be very careful about, a landmine. It's a risky move. I've seen this happen several times, that a student sees an integral, and the integral looks like it would be susceptible to a symmetry argument, and they try to give me a symmetry argument, and the thing is, it turns out the function is not actually odd, right? Or the domain's not actually symmetric, or something like that. One of the essential ingredients just doesn't work. So what do I do in a situation like that, right? The question was for students to compute an integral, certain integral. They give me an argument that not only doesn't work, but it's in a direction in which there is no hope for it to work. They are straight up barking up the wrong tree. So here's the ugly reality. A student that does so hasn't made any progress toward an actual solution, right? And keep in mind, that's where partial credit comes from. We're looking for progress you've made toward an actual solution. In other words, progress demonstrating you know how to actually solve part of this actual problem, which requires that the direction you've gone actually leads somewhere useful, right? So the dangerous thing, you can think you got full credit on the question, but you made an oops in one place that deluded you into thinking you had an answer, when in reality, again, totally barking up the wrong tree, and then there is no progress toward an actual valid solution that I can use as a basis to give partial credit. So it's dangerous, right? It is for sure dangerous. So if you do give a symmetry argument, and again, I encourage you to do this. This is powerful and valuable. If you do, double check it, right? Be ultra sure. Think it through. Take the moment. You just saved yourself loads of time by not having to work out the ugly side of the integral. Spend some of that double checking and making sure that your reflection is right. Right? Make sure that the domain actually is symmetric the way you think it is. Make sure you're not accidentally using two different lines to make your symmetry arguments. Just be careful, because it's a crying shame when somebody steps on this landmine. I hope everybody understands. Does that all make sense? Okay. All right, here's one. This is an example of what not to do. This is a hypothetical exam question and a hypothetical student response. And you can see the student gets, what's that, 4 out of 10 on this question. It's not good work. So let's break it down and see what the problem is. The student's asked to compute this integral. They note correctly that the domain is symmetric. True, it is symmetric in a sense. They note correctly that the function has an odd symmetry. That's true in a sense, right? But this student, having done that, let's see if I can, first of all, I need to be in this mode. Here we go. Let's look at how much of a complete symmetry argument did the student give me. The student has correctly observed that the function was odd. The student has correctly observed that the domain was symmetric. But there are gaping holes in the student's argument. They never told me what line of symmetry they're using. In some sense, they haven't really observed any symmetries of the domain at all. They just claimed that there is one. It's not good enough. What line we're using is really important. We've got to establish that for the record, and so make sure you document that so you can get those points. Yeah.
If the line of symmetry isn't on the axis, how exactly?
Yeah,
I'm going to show you a couple of examples,
okay.
or at least one example, okay. And then there's another example on the homework that's going to come up that. I'll address that now. Yeah. Okay. make sure you tell me the line of symmetry. The student didn't tell me the line of symmetry. The student left free money on the table, right? All you got to do is just tell me what line. Just tell me, right? It's real easy. The student, of course, also didn't write down how the reflection works, didn't demonstrate that the function is odd. It's not at all obvious that this function is odd. And if so, over what line, right? There's a lot missing in what this student has done. So again, the student would get 4 out of 10 if that were a 10-point question. And so don't make this mistake, right? Make sure to go through the list. Make sure to give me you give me what I want, I'll give you what you want, right? Nice and simple. Okay. All right. Okay. Here's another example. This is a nice example of how it's convenient sometimes to just be able to say the domain is symmetric. Oh yeah, question. Sorry.
For the previous example,
yeah.
How would you find the line of symmetry for that?
Oh well, that's a whole thing. You got to think that through. You got to think about what the shape of your domain is. Look at it. Think about all the different possible lines of symmetry. There's 4 of them, by the way.
Oh wow.
Yeah. And then you also have to think, for each one, or whichever one you plan to use, what is the corresponding reflection, and is your function actually odd as you need it to be, right? So there's a whole discussion there, and I don't have time to do this in detail, but there are details that have to be filled in. Yeah, right. Okay. Yeah.
For the symmetry part, is it just the fact that the bounds are symmetric? Like
Nope. It's a geometric thing. It's not an algebraic thing. So you got to draw a picture of this domain, right? And then look at the picture, and then geometrically see that if you reflect it over there's several different lines that will actually work, right? 4, if I remember correctly. And you got to make the geometric observation. Yeah. All right. Okay, next example. So, I hope you all remember all of your high school algebra, maybe a little calculus, whatever it is you need to be able to plot these curves. Again, that's kind of fundamental to what we're doing here, so make sure you can do that. This is what the domain looks like. It's bounded by those curves. And I'm just going to make the geometric appeal. I think this is pretty clear geometrically. And this is good enough for our purposes in this class. But that domain, I keep missing the little, come on, man. There we go. Is symmetric over that line. And you notice all I said down here is the domain is symmetric over that line. Now, for your own possible curiosity, I also included some discussion of how I know it. This is just for your possible curiosity. Reminder, it is not required. You don't have to justify why the domain is symmetric over the line in question. But you do have to state it. And if you're curious how I knew, then this is an outline of kind of how I did that. Yeah?
So to get the line of reflection, you have to grab it.
You got to draw the picture. Yeah, right. It's a fundamentally geometric feature, and so you pretty much got to draw the picture.
Okay.
Yeah. Okay. Now, if we're going to use this line, we're going to need to be able to talk about the reflection, because we're going to need the reflection to make an oddness argument. So how does it look if I want to reflect over this line? If I have some point here, and if I reflect over that purple line to get its reflection point there, how's that work? And this is a weird one, right? This is highly non-obvious how to do this reflection. It's not a simple matter of just negating the position vector. It just isn't, right? If I negated the position vector, we'd be way over here or something. That's obviously not it. So what's the deal? Here's my take on it. I think this is a clever little trick. Somebody showed this to me. I'm showing you. I'm not expecting you would dream this up on your own. But here's a big idea. Your input point there, it's hard to see how the point will reflect, but I think it's easy to see how this, what I call rectangular frame, will reflect. Right? So you just think about these little line segments that kind of document what the x and the y there actually are. This is x and that's y, right? Yes?
Let's say we're going through our calculations and then we see like it's not odd.
Yeah,
so
try a different line.
It's not symmetric.
Not over that line.
Let's just like theoretically say there's just one line.
Okay.
Can we just say like, and conclude that like the integral is not equal to 0, or
no?
Do we have to do it for all of the conditions? Like, do we have to go through all of the conditions?
If the oddness fails, all that tells you is that the symmetry argument fails.
Yes.
That doesn't mean the answer isn't still 0. The answer might be 0 by coincidence. That totally happens, right? But the symmetry theorem just doesn't apply, and it doesn't apply at all. It doesn't apply to ensure that it's 0, and it also doesn't apply to deny that it's 0. It doesn't do anything. Okay. Yeah. Does that make sense? Mm-hmm. Okay. So this point, again, hard to see how that point reflects, but this green line right here, this little horizontal green line that I claim represents kind of the x coordinate part of that point, I think it's easy to see how that reflects. This is a 45-degree line that we're talking about, and horizontal will reflect to vertical. And keeping in mind, again, that our line is that 45-degree angle thing, like so. And then likewise, the vertical little blue line there is going to reflect to a horizontal line like that. And so you can just kind of keep track. Let me zoom if I can. There we go. You just kind of keep track of, okay, well, if that's x, because it's in the positive x direction, then this, okay, well, yeah, but that's in the negative y direction, so that's just going to tell me that that's a minus x, and et cetera, et cetera. And you can just straight up see that the reflected point here, that reflected point is minus y comma minus x. Everybody see how that works? This is just an example, right? Not every reflection is going to be like this. Sometimes you're reflecting over an axis, in which case the reflection formula is easy, like we did here, right? Sometimes it's over a different line, in which case it's going to break down differently, like this one. They're all different. And there's an endless discussion of considering how to do this for all possible lines, and we're not going to go into that much detail. Usually when you make a symmetry argument, it's over what I'll call relatively easy lines, kind of like this sort of thing, yeah.
Does the line need to be a level set, or could it be y equals negative x?
It doesn't need to have any relation to the...
or equal or constant?
It has to be a line. All lines are ax plus by equals a constant. So in that sense, yes, so it's got to be a line.
Okay.
Yeah.
So could we write y equals negative x?
Oh, yeah. Oh, yeah, no, I don't care how you write. Yeah, y equals negative x is totally equivalent. Yeah, no, I don't care how you write it down. It's just got to be unambiguous. Yeah, right, yes.
This is just more for, like, proof. If we can show that something's symmetric, can't we assume that there is a line of reflection? Like, why would we need to show...
How are you going to show it's symmetric? I mean, the definition of odd symmetry, though, is based on the reflection. So you can't show odd symmetry of the function until you give me a reflection, and you can't give me a reflection until we decide what are we reflecting over. So yeah, you really kind of have to. You got to pick a line, write down the reflection, and then use that to make the odd symmetry argument. Does that make sense? Yeah. Yeah. No, I get it. I approve of trying to look for workarounds, right? But I don't see how there is one. Yeah, totally. Okay, all right. So let's see, what else have we got? We've got a symmetric domain. We've got the line. We've got the reflection. What else do we need to do? And I've established that the domain is symmetric. Wait, I already had the... Let's see. Okay, the domain is symmetric, reflection. Oh, yeah. So now we've got to worry about oddness. I've got to state that the function is odd, and I've got to demonstrate that the function is odd. And this is another little slightly tricky bit. And so let me be careful about this one. How this goes down is just a little bit different. Keep in mind, here's our reflection formula. And you can see I'm plugging my reflection in to my integrand function that I want to demonstrate to be odd. Oh, I keep making bad color choices. I like to reserve the green and the blue. So that's what I want to show as odd. Here's the minus y minus x that I'm plugging into it. And so again, be really careful when you're plugging stuff in. You've got to think about what is the first input and make sure to plug that in for what is naturally the first input to your function that you're claiming something about. Right? So here you can see the very first thing that I'm plugging in is minus y. When I plug that in up here, I've got to plug it in for as it is the first input, I've got to plug it in for what was the first input to this expression, and it's x. So it goes there and there. Minus y then goes there and there. Everybody see that? Yeah.
Just like a quick fun clarification. So
Yep.
on the line above when you say D is symmetric over L.
Yep.
All right, is that statement about C1 and C prime and C2 and C3?
It's about this statement D about D here is about the domain that's bounded by those curves.
Oh, yeah.
So I hear you. So yes, the observations I'm making about the curves and how the curves reflect. If you know that everything that goes into defining the domain is symmetric, then it kind of follows that the domain itself is symmetric also.
Right. No, I was more so saying, like, would those be, like, required in an argument? Or would
No.
just observe that and say that?
Yeah, so in fact, remember, the only reason that I included any of this, all of this right here, was just kind of for communication purposes, just for in case you were wondering what my thought process is. All you've got to do is actually state and be correct that the domain is symmetric. So none of this is required in the red there. Does that make sense? Yeah.
I'm kind of confused as to, you're saying that we have like the first input variable and the second one.
Yeah.
But could you write that as y plus x?
Yeah.
Minus y plus x, and then it'll switch the order.
As what now?
I'm kind of confused what you mean by, like, I understand normally we'll say the function is f of x, comma y.
Yeah.
But how do you determine?
Yeah, okay. Yeah. Sure. So, I mean, you just got to make a decision and stick with it. So, I mean, the presumption that I'm working with here is that we're writing that as f of x comma y is defined by this formula.
But that's, right? And that's just based on you saying that.
Yeah.
Okay.
Yeah. But then whatever you decide to be, let's see here, color choices. Whatever you decide to be this, that's what has to then go there. So you gotta play fair, right? So if you want to switch the x and the y here and here, then okay, fine. But that'd just be pointless weirdness. Yeah. Right. Okay. So be careful in terms of how you plug this stuff in. And so again, the minus y goes there and there, and then of course likewise this minus x, that's going to go in for where the y's are. Thus it is the second input, it goes where the second inputs go. And so that I missed, but anyway, it goes there. I keep missing. And there. So that's the kind of the trickiest part of the argument. Make sure to plug in correctly, and then a little algebra, and you got to follow through the algebra. And I know y'all are really good at algebra, so this simplifies like that, and sure enough, we have a minus sign that pops out as a result of having put the reflection in. So reflection in, minus sign out. That means our function is odd. Integral 0 by symmetry, we're all done. We avoided the ugly. Everybody happy? Oh, yeah.
Is the argument about the symmetric domain that you said, is that when the bounded domain is symmetric and the bounded domain is symmetric, is that like a defined argument? Like, can you state that generally, or is this specific?
You're talking about this argument right here?
Yeah.
Oh, I'm going to say that that's not something that's something we don't have to worry about. I hesitate to answer yes or no to your question because you said that scary word. You said always. And that means I got to have a theorem. Ooh, theorems have conditions. This is really scary stuff. That's a whole bunny hole that I don't want to go down. Right. Does that make sense? But again, keep in mind, you're not obligated to explain why. You just have to state it and be correct that the domain's symmetric. Yeah. All right. Your geometric intuition is going to totally be your guide on matters like this of deciding if the domain's symmetric. Okay. All right, here's another example. This is one of the scary examples. This is a landmine example, right? This is where a student can get zinged badly. Again, I'm a fan. I hope you all will use the symmetry arguments. They're fantastic. They're one of my favorite results in the whole class. But be careful. Yeah. Yeah, it's just a matter of the first input's got to go where the first input goes, right? So this is the first input to what I've got right here, right? Well, that's got to go where the first input goes, and the way I've written the function down here, this is f of x comma y, so x is that first input. Talk to me about it after class, and I can give you a different point of view that you might find convenient, but there are different feelings on it. Yeah. Okay. All right. Okay, again, landmine example. Oh man, this happens. Scary. Let's look at this domain. 0, 2, -1, 0, 1, 0. Our triangle has those points as its corners. Our domain looks like that, in other words, and oh my gosh, look at that, it's symmetric, right? Symmetric domain, odd integrand, integral 0 by symmetry, or so it seems. You can see the allure of that argument. Isn't that tempting? I mean, we love it when symmetry works. It's awesome when symmetry arguments work, and it's like, symmetric domain, odd integrand, and it's easy to get all pumped up and excited about it and kind of proud of yourself maybe, hey, I noticed one, right? It doesn't work. And tragically, if a student were to make a symmetry argument here, nothing they write is relevant to the solution to this problem. And the reason why is that if you look at the domain here, this domain is symmetric, but only over the y-axis. Very much. Only over the y-axis. And now if we look at the oddness, where does the oddness of that function come from? The oddness comes from the reflection being this. The oddness comes from getting an extra minus sign on your y, which means the reflection would have to literally put a minus sign on your y coordinate, which means that's odd only over the x-axis. And those are not the same line, and the theorem only works if it's the same line, and so there is no symmetry argument here at all. That's a dead end in this case. Everybody on board? Everybody see? Yeah.
I'm a little confused by how, for this example, it's symmetric. How come the first example you did, it was symmetric over the y-axis? That was fine, but now this one's not. Is it because
they're different shapes? Ultimately, yeah.
That's
okay. So I mean, I'm just going to be able to make it the geometric appeal. I mean, this is how the reflection works that would make this symmetric, right? And that's over the y-axis. And you were talking about. Oh, wait a second. Where is the? Oh, you were talking about this one.
Yeah.
So this one also is symmetric over the y-axis.
Yeah.
Yeah.
But that
I didn't understand your question.
You can do the theorem for that one, but you can't do it for the second one. And I'm just a little bit confused why.
Yeah, because the theorem requires that we use the same line for both of the symmetries, right? And that's sort of the only way that this Riemann sum cancellation is going to work. I've got to know that the terms pair up over the line, but I need them to also be odd over that same line. Otherwise, the argument's nonsense. So it's delicate. So dangerous. So watch out. Beware. Right? Don't say I didn't warn you. Right? This is a dangerous little scenario where you can totally think you're seeing a symmetry argument, but there isn't one. Yeah.
So here, can we just write explain our observation on why it's not odd, or do we have to demonstrate it algebraically?
In this example, there's no point in discussing why it is or isn't odd because there is no symmetry argument. So you don't have when you're answering an exam question, you don't have to explain which methods don't work. Does that make sense?
Yeah,
you gotta
just
find one that does. And sadly, on this example, you gotta write it as an iterated integral and crank it out in the old-fashioned way. Right. By the way, here's another obvious sort of if you're looking for an easy way to rule out symmetry on this integral. Notice that on our domain here, our integrand. Our integrand being y cubed, well, notice on my domain, that is clearly always positive. Right? Clearly positive. Y is never negative on this entire domain. So y cubed is never negative. There can't be cancellation if the integrand is never negative. So there's definitely not a symmetry argument. Okay. Please be careful. Otherwise, symmetry all you like. Real quick, same idea in 3 dimensions. In 3 dimensions, we don't reflect through lines, we reflect through planes. Every morning when we wake up and look in the mirror. Right? That's the most natural kind of reflection. That's the most personally relatable kind of reflection. So it's exactly what you think. We don't need to worry about getting fussy about how to define it. It's exactly what you think it is. We define oddness again. That reflection in gives you negation out. It's exactly what you would expect. We define a symmetric domain. Again, it's the whole Rorschach thing, right? It's when you reflect it, it doesn't change. And here's some notation if you want to write that down formally. You don't have to worry about that. It's exactly what you think it is. And we get the exact same theorem. In fact, I think I literally copy-pasted all of this when I was writing these notes. And then all you got to do is change this to volume instead of area, and this to a triple integral instead of a double. It's otherwise exactly the same theorem. Okay, so same punchline, odd integrand, symmetric domain, integral is 0. Make sure to check both of these conditions, by which I mean make sure to check all 5 of the detailed list of requirements that I gave y'all. And again, make sure you're using the same plane for both. It's really, really very, very similar, if not exactly the same. So here's a nice example. This will be our last thing for today. Suppose I'm doing an integral over the unit ball. Nightmare. Square roots are just everywhere. Now, clever idea. I'll do it in spherical coordinates. Cool, right? I like it. Definitely better. Now you got tons and tons of trig. You know, not that it can't be done, right? But that's it's likely to be annoying, right? So that's a hard one. But check this out. Let's think about the xy plane. Horizontal plane. When you reflect through a horizontal plane, you're just going to negate the z coordinate. So the reflection is easy to write down. It's the unit ball. The unit ball is symmetric through lots of planes, including the xy plane. And I claim the integrand's odd, and the reason I know the integrand is odd is because, again, all I got to do is add a minus sign right there, and you can see that gives you the minus sign that you need. Integral 0 by symmetry. I don't have to deal with square roots. I don't have to deal with spherical coordinates. I don't have to deal with trig. 0. Okay, out of time. Wait a second. Are we out of time? Oh, we have a minute. Okay. Yeah.
So this one, do you not have to draw it to see the symmetry?
Yeah, if it's really, really obvious, unit ball, I mean, that's pretty clear, I think. So if it's painfully obvious, yeah, I'm not going to be uptight about it. Yeah. Okay. Last question. Yeah. I can't hear you. Let me just wrap it up and let people go, and we'll talk in a second. Yeah. Okay. See y'all later. Have a good one.